in the last video, we saw the action potential that we see in the intrinsic conduction system, but what really is the intrinsic conduction system? So it is the independent of any neural stimulus to cause it to happen. It can be influenced by neural stimuli or chemical stimuli, but does not require it to happen. And then coordinated activity of the heart produced by the intrinsic conduction system and the gap junctions. So they are cardiac muscle cells, cardiomyocytes, but they are non-contractile and they're specialized to initiate and distribute the impulses through the heart, have an unstable resting potential, continually depolarizes to the threshold. So there's the funny channels. We just call them slow in my class, but there's the funny channels, and then we have the calcium channels opening, and then the potassium channels. I simplified it more than what you guys have, but anyway, that's what's happening. So if we take a look at the cells that are involved, we have the SA node, and then we have the internodal pathway in the Bachmann's bundle over here, not labeled in this diagram, taking the signal to the AV node. At the AV node, we're going to hold on to the signal for about 1/10 of a second, and we'll talk about that in just a minute. And then we go down to the AV bundle, or the bundle of His, and then we're going to split when we get to the interventricular septum into the right and left bundle branches, which will then curve around and become the Purkinje fibers, or the subendocardial conducting network, which I would much rather just refer to it as the Purkinje fibers. All right, so in your study guide, wire gap junctions and intercalated discs important in the conduction system, because as these depolarize, the sodium at each one of these stages will then pass through the gap junctions and into the to the cardiac myocytes, the ones that are going to contract, and then allow the actual muscle contraction to occur. Okay, so we have which type of heart cell is being utilized. Those are the non-contractile cardiac muscle cells. SA node is the pacemaker of the heart, because SA node is the one that depolarizes the most rapidly. So from there, you'll generate the greatest number of depolarizations in a minute, and the SA node likes to fire about 60 to 100 times in a minute. If the SA node were damaged or the signal were blocked, then the AV node would take over. So we have up here that 60 to 100 beats per minute is what we refer to as the sinus rhythm of the heart. And if anything were to happen to the SA node, then we would get a junctional rhythm here at the AV node, because that's the junction between the atria and the ventricles. The AV node does not depolarize as rapidly as the SA node, so you're going to get a junctional rhythm between 40 and 60 beats per minute, which is enough to keep you alive, but not enough to if you're going to go run a marathon or a sprint. Actually, you'll probably be in bad shape if you're trying to do something very quick, heavy lifting or running a sprint or something like that. And then sometimes if we get some ion imbalance out here around the heart, hyperkalemia, hypocalcemia, or hypercalcemia, sorry. And the Purkinje fibers are wanting to fire at their intrinsic rate, which is less than 40 beats per minute. Sometimes you'll get little extra spots in here where the Purkinjes are within the ventricles, and they fire on their own. Maybe caffeine will affect them, something that's in a Red Bull besides the caffeine. Just those energy drinks, you guys, you just don't even want to take. And so then we'll develop what are known as ectopic foci. So an ectopic focus is where another part of the heart depolarizes. We may get some SVT, some supraventricular tachycardia. So we get some other areas up here causing the ventricles to contract really rapidly. But anything that's going to cause the heart muscle to contract that is not in the proper sequence within the intrinsic conduction system then would be considered an ectopic focus. Okay, then if so, we can read through those. Oh, here's why the impulse is delayed. 1/10 of a second at the AV node is so that the atria can finish their contracting, respond to the stimulus coming from the SA node, and then finish their contracting, push the blood down into the ventricles, and close the AV valves. And why does it take 1/10 of a second to make it through the AV node? Because the fibers are smaller at this point with fewer gap junctions, so the sodium doesn't pass through as rapidly. It's kind of like merging 4 lanes on the freeway down to 2. Then we go to the AV bundle, right and left bundle branches, and the Purkinje fibers. And then we can take a look at when they fire. So we have that pacemaker potential in the SA node, and then we have, this is going to be the regular cardiac muscle contraction action potential that we saw before, like we see here in the ventricles. And then the AV node also has its own pacemaker potential, and notice that it's not as steep, that it would take longer to get to threshold, and that's why it will only fire 40 to 60 times a minute instead of 60 to 100 like the SA node. Okay, I don't think we need to go into that or that. And there's ectopic foci, heart blocks. If you have damage to an AV node, for example, sorry, I just lost my thought. And the sodium is not making it through as quickly or as well, then you'll get, and we'll see in an EEG or an ECG in just a minute, we'll get some non-firing of the ventricles. And when that doesn't fire, typically it's the AV node that's been damaged, or there's some problem there. And so we want to be able to get those ventricles to contract all the time. We want to couple what's happening with the atria to the ventricles, and we may have to put a pacemaker in the event that we have heart blocks. Don't want a total heart block. Partial heart blocks are bad too, but we want to make sure that the ventricles are being told to contract, and then we put in a pacemaker. Okay. So let's go into I'm going to just let you go ahead, because I don't have, in my PowerPoint, I don't have the cardiac excitation contraction coupling, but it's going to be essentially what we have within the skeletal muscle, with just a little bit of differences specific to cardiac muscle. But if you have any questions about that and you need me to go over that before your test, then make sure that you let me know. All right, so if we take a look at electrocardiography, so here is one measurement of the electrical activity of the heart. And so I'm not going to go through a lot of information about this, but essentially just want you to know what's going on here. So when the atria depolarize, and first with electrocardiography, make sure that you know that we are not tracing where the signal is going through the heart. All we're doing is looking at changes in the electrical activity that's happening within the heart, and we're looking at the overall electrical activity. We can't track the electrical activity that happens from the SA node, the internodal tract, to the AV node, to the AV bundle, and so on. This is just a snapshot of the changes in electrical activity in the heart itself. So the first deflection from what we call this isoelectric line right here is called the P wave, and the P wave represents atrial depolarization. So as the atria are depolarizing, not contracting, but depolarizing, then we're going to see this upward deflection based on where is the snapshot that we are taking of the heart. And this information in the study guide goes into that in a little more detail, but I have a hard time thinking that you would need to know that in super great detail other than this. So we have atrial depolarization. Then we have what's known as the QRS complex, which is ventricular depolarization. as the signal makes it all the way down to the bottom of the ventricles and then starts contracting, because remember, contraction from the atria is going to start from the top of the atria down to the bottom, but ventricular contraction is going to start at the bottom and come up to the top. And so the QRS represents ventricular depolarization, and then we have ventricular repolarization, which is the T wave, as the ventricles return back to resting membrane potential. Now, as you know, as you can see, there's no atrial depolarization, and a lot of times people will say it's lost in the ventricular depolarization. But what if I don't have any ventricular depolarization? What if I have a heart block and I will get P waves but no QRS? There still isn't anything here. So if I were to stop the QRS complex from happening, we still don't capture the atrial repolarization. So it will happen time-wise within the QRS complex, but we just don't see it. It's just not significant enough for it to be recorded on an ECG. So remember, P wave, atrial depolarization, QRS, ventricular depolarization, T wave, ventricular repolarization. Here's just another example of what's going, our diagram of what's happening. So here we can see that initial depolarization of the ventricle, or the atria, sorry, represented by the P wave, and then we have complete, and then this time period in here is when the AV node is going to receive the signal, and then it'll propagate that down to the bottom of the heart, and then we'll get the QRS, and then we get this resting time while it's all depolarized, completely depolarized, and then as it repolarizes again from the bottom of the heart, then we get the T wave. So this just shows some examples of different rhythms. What I was talking about with the heart block, I'll show you how we can't see P waves in just a minute. So one thing to remember with the electrocardiography is to know who's driving the bus, and in other words, who is initiating the rhythm. And if we use this, we can tell the depolarization and repolarization are happening, but the lines on here also tell you the rate at which your heart depolarizes. And so here in this normal sinus rhythm, we can tell that it is the SA node that's driving the bus, because we have a P wave, QRS and T, and a P, QRS and T, and we have very many. The rate is very rapid here, and so we know that the SA node is firing. Now, if we go down to the second one, there's two ways to know that the SA node is not driving the bus anymore, that it's the AV node driving the bus. One is there's no P waves, okay, at all, and the rhythm is very slow. It's much slower than what we saw in this sinus rhythm up here. So we know that the QRS, the AV node is driving the bus. So no P QRST, no P QRST, and again, lots of time between ventricular contraction. Now, in the second degree heart block, this means that not every atrial depolarization, not every SA node firing is making it to the AV node and through onto the ventricles. It's getting stuck at the AV node. And so here we have, in this, we have a QRS and a T, and then we have a P, QRS, T, P, and then no QRS. Now notice we also don't have any atrial repolarization either here, so that's how we don't see atrial repolarization in ECG. So P wave, nothing. So then the P wave fires again, because remember, it fires at its own 60 to 100 times a minute, so it doesn't care what's going on at the AV node. It's not going to wait. It's going to go ahead and fire again. And this time it fired, and there was enough buildup, and more sodium got through, and so then we got the QRST P, and then nothing. P QRST, P QRST, or P, and then P QRST. One other rule of thumb with electrocardiography is there should be a QRS for every P, and there should be a P for every QRS, and that would ensure that we have normal cardiac electrical rhythm. And then the last one down here is ventricular fibrillation. So the ventricles are doing whatever they want, and we don't have any sinus rhythm, and we don't have any regular contraction, and this is when we defibrillate. If you were to flatline, if this were straight, we are not going to use a defibrillator on you, even though every TV show and every movie you've ever seen in your life, if you flatline, they shock you back to life. Nope, we cannot jumpstart a heart. We can inject you with epinephrine or norepinephrine to increase the permeability of the SA node to sodium so that it'll depolarize again, but jump-starting your heart is not a thing. When you're in fibrillation, and that's fine, we do use a defibrillator, but please don't tell me that we use it on a flat line. So here is fibrillation, and so what we want to do is shock the heart into complete contraction, and then hope that the SA node will kick back in again and produce the P wave with the atrial depolarization, and then start everything. And so that's what we're doing. We are just slapping the heart with electricity to get it to stop, and then allowing the SA node to take over again. Okay, so I think that's all that I wanted to do now. So we'll go into cardiac cycle in the next video.